Hi students, it's Professor Waite and we're here with lecture 6. Hopefully you all are enjoying the technical conference. We will still proceed as per schedule. This lecture is covering Thursday's material. We will still have homework due on Tuesday, January 31st, and then our first exam will be on February 2nd. I've also listed here homework 4, which isn't due until next Tuesday, the 7th. But the material that these problems cover will be some of the material that we have on the exam, so it would be a good idea to get started on those early. Although they aren't due until after the exam, I would recommend you do them before the exam, which will help you know and understand that material a little bit better. And we will cover those topics on Tuesday, the 31st. When we start talking about ideal gases and things like that. So the exam will encompass all of chapters 1, 2, and 3, and then we'll start chapter 4 after the exam. Today we're talking a little bit more about phase change, and we're looking at the diagram. So previously we just touched on the idea that you can go from a solid to a vapor in one step without going through the liquid phase. And we've talked a lot about different types of phase changes and what they mean and what they're called. So we're going to look at some property tables and diagrams that actually demonstrate and show that what's happening physically. Because you can't always just go from a solid to a vapor. There's certain conditions that have to be met before your material will sublimate. By way of review, this is the temperature and specific volume diagram. And if we were to plot all these lines of constant pressure, we would get something that looks increasingly more like a dome shape here in the center. These lines of pressure are increasing as we go up toward the critical point. And the critical point represents where a saturated liquid and a saturated vapor are actually simultaneously the same state. And it's a somewhat nebulous state that it's not always clear what that substance is. So as I mentioned before, it's kind of interesting to look at, kind of interesting to study, but it's also a point that we want to try to avoid when we're designing engineering processes, because it can cause problems to operate at or near the critical point, because you get undesirable effects in your machinery or in your systems. As the pressure increases, the boiling temperature also increases. So if we're operating just at standard atmospheric pressure or below, then the boiling temperature will be lower than 100 degrees Celsius. And if we are operating at a pressure that's higher than atmospheric pressure, then the boiling temperature increases. And the critical point occurs at a very specific point. It's at a temperature of 373.95 degrees Celsius and a specific volume of 0.003106 for water. And this point will be different for different substances, but that is the critical point for water. These saturation lines are those that indicate or show us that we're operating in the liquid vapor mixture region. And we'll do some more examples in the property tables where we look at finding properties in that region and how it affects our system. And then this line that connects all of the saturated liquid points and the saturated vapor points is a dome shape, and we do call it a dome. And when we're talking about being under the dome, that means we're somewhere in this saturated liquid vapor region. And again, it's important to know whether you are in a superheated region or a subcooled region, or if you're operating underneath the dome in the saturated liquid vapor region, because your property values will change depending on where you are, and the characteristics of the fluid that you're working with will change as well. Because as we learned last time, in the underneath the dome, temperature and pressure are dependent. And temperature is an isothermal, or phase change is an isothermal process. So the temperature is constant, the pressure is constant during that process under the dome. Again, the critical point is where there is really no distinct phase change occurring. And so the critical temperature And the critical pressure are those temperature and pressure at which that occurs for a specific fluid. Similarly, the critical point at specific volume. And all three of these values are given for different substances. That's in table A1 in the appendices. You can pause the video and look at that if you want to take a look. And we do use these values later as we're formulating equations for ideal gases. So they are important both to avoid when we're designing processes, but there are characteristics of the fluid at that point that allow us to approximate or analyze or treat fluids as an ideal gas when they're well above that point. So, and we'll get into that more in the next lecture, but that's one of the reasons why we want to know where they are. There's also two videos. These links were given to you in the email that I sent out with this video link. And it's just demonstration of the critical point. One of these videos I showed in class already to my second section, but they're short enough that you can watch, and it's just kind of an interesting thing to see what happens at the critical point. We can plot our properties on a TV diagram. And again, everything under the dome is considered the saturated liquid vapor region, meaning we're undergoing a phase change process. If we're on this line here, it means we are a saturated liquid. If we're on this line here, it means that we have a saturated vapor. And then everything to the left of that is the compressed liquid region. Everything to the right is the superheated vapor region. And if we're looking at it on a TV diagram, the pressure is constant, and the lines are represented here in this manner. They always go from left to right with an increasing slope or a steep slope in the compressed liquid region, meaning that the volume, the specific volume, does not change very much for a change in temperature. They are flat through the saturated liquid vapor region, meaning that temperature and pressure are dependent and constant as we undergo a phase change process. And then the line shallows out a little bit. The slope is not quite so steep because the specific volume changes in a greater manner than it does for a liquid, as we have a vapor that is continuing to expand as we add energy or heat to the process. We can also plot this on a PV diagram. So now we're looking at pressure and specific volume, and then we have lines of constant temperature. So again, there's this flat line through the saturated liquid vapor region that represents constant pressure and constant temperature during that phase change process. But now we have the temperature is decreasing with increasing, or I apologize, the pressure is decreasing with increasing specific volume for a given temperature. Okay, so if you undergo some process at a constant temperature, then the pressure will decrease. We will have a constant pressure, constant temperature process that's in the boiling region, and then the specific volume will continue to increase as the pressure decreases and we undergo that boiling process. So this is another way to cause something to boil. You can increase the temperature and hold the pressure constant, or you can decrease the pressure and hold the temperature constant. If we want to include the solid phase, so this is the same dome before. This is the saturated liquid vapor region. Here we have a superheated vapor. Here we have a compressed liquid. This also shows the solid phase as well as the phase change from solid to liquid. So as we melt or as we freeze, solidification or melting process, that can also be represented on a PV diagram. The unusual thing about water is that it actually expands as it freezes. So this diagram right here, you see there's this kind of a dash line. We're going to look at a 3D version of this in just a minute that makes it a little bit more clear. But because the substance is expanding upon freezing, it has a little bit different characteristics. And not every liquid does that. Water is actually unique in that regard, that the volume increases as it freezes. Most substances will actually decrease as it freezes, but water is unique in that regard. And then there's the triple line, which represents a state where all three phases exist at the same time. So we'll have a liquid, a vapor, and a solid all at the same time. It's called the triple line on a PV diagram, but if we look at it on a PT diagram, plotting pressure and temperature, it's actually a single point. So you can imagine that if we turn this diagram, then we would see it as a single point rather than a line. And at pressures below this line, weird stuff happens. So a solid goes directly to a vapor. That would be like an example of the CO2 sublimating that we saw in class. The solid CO2 or the dry ice was sublimating. So if you look at these diagrams and you're interested in knowing what process you would need to follow if you wanted to have sublimation, or if you want to avoid boiling, or whatever it might be, you could look at where you are in the space of this diagram. So let's say that you currently are in this region here, and you wanted to vaporize your substance. Well, then you would know you could hold the pressure constant, but just allow the specific volume to increase, and that would be possibly due to a temperature increase or something like that. So these are useful diagrams so that you can understand how to undergo a specific process, at what pressure and temperature your material is going to be in a liquid vapor state, or it's going to be solid. And these diagrams exist for every material that we use in our engineering design and analysis, and it's just kind of useful to look at it in this matter. So if you want to see kind of a cool video, this is also included in the link that I sent in the email. It shows all three substances at the same state. So you have a solid and a liquid, boiling, and vapor. It's kind of weird, and so the process that it undergoes to get there has to pass through or along the triple line in order to have all three substances present at once in the same material. And it's not something that would happen in real life, like at ambient conditions. It's not generally something that that you would see, but in laboratory conditions, you can make it happen. You can artificially cause this process to happen by setting the conditions right, so that you're acting on the triple line. So as I mentioned before, if we look at the PT diagram rather than the PV diagram, the triple line occurs as a single point. It's like we're looking at this 3D cube on its end. So at the triple point, that is where we would have a solid, liquid, and vapor existing in the same state. So at a certain pressure and a certain temperature, that will occur for a given substance. And again, that triple point, similar to the critical point, is given as a value of the material that we're working with. So regardless of the ambient conditions, pressure and temperature, specific volume, there's a certain point at which that will occur. And you can see again also on this diagram, there's the critical point. So if we were to look at that in 3 dimensions, so now we have pressure, volume, and temperature. We're plotting like a 3D surface. So this is an example for a surface that contracts upon freezing. So this would not be water. Water would be something that expands upon freezing. But we can see that all of the potential possible combinations of pressure, volume, and temperature for a given substance have to lie somewhere on the surface of this 3D diagram. Okay, so if you decided you wanted to have a pressure, a volume, and a temperature that was here, well, you would never be able to achieve that. That it's not possible to have that pressure, temperature, and specific volume all at once in your substance. So this is helpful to us because we can again use property diagrams and these known quantities to find where we are in space. So if we know the pressure and the specific volume, we can always find where we are on this surface, wherever it might be. However, if all we know is the pressure and temperature, we might know that we're somewhere along this line, or this line, or this line, but we would need to actually fix the state using a specific volume. because for the same pressure and temperature, we can have multiple specific volumes under the dome or in the saturated liquid vapor region, because pressure and temperature again are dependent during that phase change process. So going back to property tables, I've had a few questions about this in email, and I hope that you are working through these, that you're figuring out how to look things up. We're going to do a lot of examples today, so it should help you out. But let's just review again that if we are looking at the saturated liquid, saturated vapor state, so for water, that's table A4, we have the first 4 columns here. So we have temperature, pressure, and then the specific volume of the saturated liquid state, and then the specific volume of the saturated vapor state. So if we know the temperature, and we know that our specific volume is somewhere in between these two numbers, so this gives us a range, then we know that we're somewhere on that line, that we're in between the specific volume of a liquid at that temperature and of a gas at that temperature, so we must be somewhere along that line if we're given a specific volume in the problem. Similarly, if we're given this pressure and given this temperature and told that we have a saturated liquid or told that we have a saturated vapor, then we automatically know the pressure, because that's fixed again when we're operating under the dome during that phase change process. So these subscripts again, F is for fluid, G is for gas, and if we have a subscript that's V sub F G, that means V sub G minus V sub F. Okay, so we just subtract these two. And for a specific volume that is not given to us in the table, the VFG, we have to do the math, VG minus VF. But for other properties like internal energy and enthalpy, it is given as a third column in between VF and HF and HG. So let's talk about this term enthalpy again. And enthalpy is the sum of 2 different terms that often occur in these thermodynamic relationships. And this is something that occurs over and over and over, because as we're looking at an energy balance, these terms come up, because one is the internal energy, and then the second one is the flow energy, okay, or the energy due to this flowing fluid that has some pressure and specific volume associated with it. So we're bringing energy into our system both by having some internal energy on our fluid, but then also as our energy flows or expands, then we have some additional flow energy that occurs. Now during a phase change process in a closed system, we don't have any flow necessarily. However, we do have expansion of gases. And although there is not specifically a flow associated with that, or maybe a mass flow rate, we do have a pressure and volume relationship that as this gas expands, if the pressure is allowed to remain constant and the gas is allowed to expand freely, meaning it's in a piston cylinder device and it's not somehow restricted in a closed cylinder, then we can easily calculate this term just by knowing how much the gas expands to fill the space. Okay, so again, this enthalpy is also called the latent energy. It's the latent energy of the fluid. And in particular, if we're looking at a phase change process, the H sub F G, which is the difference in the enthalpy from the gaseous state to the fluid state, is how much energy is required to vaporize that fluid, or how much energy must be removed in order to turn a vapor back into a liquid or liquid water. And if we look at these units here on P times V, that's kilopascals multiplied by a meters cubed term, or a meters cubed per kilogram for the specific volume. We can show that a kilopascal times a meter cubed is equal to 1 kilojoule. And I think I've done that earlier in class, but you can look also in the unity conversion ratios in the back of your book, and you will see that a kilopascal multiplied by a meter cubed is actually equal to a kilojoule. So that's a unit term of energy. And then if we're looking at specific volume rather than total volume, we have meters cubed per kilogram is equal to 1 kilojoule per kilogram. Okay, so it's just energy divided by mass. So let's do an example. In this particular example, we're going to look specifically at how much energy is required to go from a completely saturated liquid state to a completely saturated vapor state. So in other words, we're vaporizing this fluid, we're undergoing a phase change process, and we want to know how much energy is required at a given pressure. To set up the problem, we have a mass of 200 grams of saturated water, and we completely vaporize it at a constant pressure. Now, in order for that to occur at a constant pressure and to be able to somehow figure out the volume and maintain a property process, that's usually done in a piston cylinder device. So if this piston is free floating and it's allowed to expand as the gases expand, then we can add heat to this system and the gases expand freely without any additional restriction. We're assuming that this pressure is balanced by this piston on top right here. So the pressure is maintained constant while we add energy to this system. And because it's a phase change process that's occurring along the saturated vapor line at a constant pressure, then we also know that the temperature is constant too. So let's just look at this solution. So the pressure is held constant, and it occurs along this saturation line at 100 kilopascals as given in the problem. So we can go to the property tables for 100 kilopascals and look that up. So let's just go now to the appendix, and we want to look at table A5 because it's in terms of pressure. So if we're looking at table A5, and this column here is in terms of pressure, we want to look at what happens at 100 kilopascals. So all of these property values are those that we find at 100 kilopascals. Okay, so our first part of the problem is we want to determine the volume change, and then the second part of the problem is we want to find the amount of energy that's transferred to the water. So immediately I know that if I want to look at a volume change, I'm going to have to look at these terms here. This, I don't know how to get rid of that highlighting. Okay, so we're looking at the saturated liquid and the saturated vapor specific volumes. So we're going to need to look up these property values, V sub F and V sub G. We also, because we're looking at the amount of energy that is required to vaporize that substance, we're going to look at H sub F and H sub FG, H sub G. So this HFG term is actually the amount of energy required. So let's go back to the presentation and look at the solution. So we look up these property values from the table, V sub F, V sub G, and H sub FG. So the volume change is equal to this VG minus V sub F multiplied by the mass. Because if we want to look at the total volume and not the specific volume, then we have to multiply through by the mass. So it's just 200 kilograms multiplied by the difference between those two, which gives us 0.3386 meters cubed. And again, we looked these property values up in table A5. Then the amount of energy transferred to the water is equal to this latent heat of vaporization. So this enthalpy, H sub Fg, is the amount of energy that is required to go from the fluid state to the gaseous state, or in reverse, that would be the amount of energy that is removed in order to make that phase change process occur. So again, we multiply through by the mass because we want the total amount of energy transferred to the water, not the energy per unit mass. And we just multiply 0.2 kilograms by this H sub Fg term, and we find that the total energy is 451.5 kilojoules. So again, if we look at the property tables, we would be able to see the the values that were looked up, and it allows us to just complete this problem quite easily because that information has already been tabulated. There aren't any equations that we have to worry about or things that we have to look through. So that's nice for us. What gets a little bit more complicated is now, up until this point, we've only looked at things when they were either, on the saturated liquid line or the saturated vapor line. But we do know that things can occur in between, and we have previously looked up property values where we're given a saturated or we're given a specific volume or something here, and then we just say, okay, it's a saturated liquid vapor mixture. But we don't really have any additional information about how far it is along this line. So we know it's somewhere on that line, but in many cases we want to fix exactly where it is along that line and be able to look up the other property values. So if we're given specific volume and given temperature, we can use that knowledge of the specific volume to tell us where we are along that line. And then there's an equation that helps us or defines where we are, and then allows us to apply that equation to other property values to determine what they are. So during this phase change process, we're going to have part vapor and part liquid. And when we're given a specific volume, it's the average total of those two parts. Okay, so you can imagine that at a saturated liquid state, we have one specific volume. And then as some of this liquid vaporizes, the volume is going to increase up until the point that all of it is vaporized. And I'm getting a little happy with the drawing on the slide, but you kind of get what I mean. So this process here takes us from a smaller volume to a larger volume. And at every state in between, or every position in between, we have an increasing amount of saturated vapor relative to the amount of liquid that we have. So the amounts of the saturated liquid will change. We have less and less and less liquid, more and more and more vapor. But the properties of those individual substances does not change. So we may have this much saturated liquid and this much saturated vapor, but the property values of this liquid are still the property values on the line. And the property values of this amount of vapor are still the property values as they would be if they were on that line. Okay, but because we have a mix, we come up with some average property value that takes into account the entire substance. So the vapor plus the liquid, instead of looking at those individually, that we have this amount of saturated vapor with a property value of this, and this amount of saturated vapor, this is liquid, with a property value here, we just come up with like an average property value that takes into account both the liquid and the vapor state. Okay, and this is called, or this is helped to be defined by the quality. So the quality is the ratio of the mass of vapor to the total mass of the mixture. Okay, so as I've been saying, as we're moving along this line and our specific volume is increasing, certain amount of our substance is in the liquid state and a certain amount is in the vapor state. So if we know or can figure out the mass of the vapor and the total mass of the substance, then we can determine what percentage or proportion of that is actually in the vapor state. So that is the quality of the substance. And again, we can use the same subscripts, that M sub F is equal to the mass of the liquid and M sub G is equal to the mass of the vapor. So then, knowing this information and having this quality term, we can find these average property values for any of the properties that we want to determine. So specific volume, or enthalpy, or internal energy, or entropy, they can all be substituted into this equation. So we can look up H sub F, for example, from the property table, and H sub Fg. And if we know or have calculated the quality, then we can come up with some lump average that quantifies the characteristics of the fluid in both the liquid and the vapor state. So it's just like this lump property term that allows us to look at this mixture as a whole rather than only being able to study the individual parts. So let's just look at that, and hopefully this example will make things a little bit more clear. We have a 100-liter vessel containing 5 kilograms of water at a pressure of 200 kilopascals. So there are 4 things that we want to determine: the temperature, the quality, the enthalpy, and then the volume occupied by the vapor phase. So let's just look at that and think for a minute how we would determine this, how we would go about solving this problem. Okay. So we're given a volume, a mass, and a pressure. We don't have 2 independent properties yet. We have pressure and we have total volume, but we would really like specific volume. So to fix the state, we have to divide the volume through by the mass and convert from liters to meters cubed, and we get 0.02 meters cubed. So now we know the pressure. Now we know the specific volume. We can go to our property tables and we can look up at this pressure of, what was it again? 200 kilopascals. We can look up the specific volume. So if we look at the values for specific volume here, V sub F and V sub G. We calculated the specific volume to be 0.02, I believe it was, which lies in between these 2 values. Okay, so at 200 kilopascals, if we have a specific volume that is in between these 2 values, then we automatically know that we're operating under the dome along a saturated liquid vapor line, and that our temperature has to be the saturation temperature. So from table A5, at the pressure of 200 kilopascals, we can find the specific volume is equal to 0.01061, and in the gaseous state it's 0.88578. So we've looked up these property values. We'll use them in a minute. V is in between those 2 values, so we are in the saturated liquid vapor mixture region. Okay, so therefore then our temperature is just the saturation temperature at that given pressure of 200 kilopascals. Okay, and hopefully that makes sense. If you're still having trouble seeing it at this point, please come talk to me in my office and we'll go through some of these examples more clearly. Okay, now we want to know the quality. So we know our average property values. So V average is equal to this 0.02 meters cubed per kilogram. So we've just calculated based on the volume and the mass, what is this lump sum average of the fluid in that container. Using this information and the idea that quality is equal to V minus VF over VFG. So if we were to rewrite the equation for quality, instead of having our mass of the vapor over the total mass, we now have this other term in regards to specific volume. Okay, so we can calculate our quality is equal to 0.0214, and this is a unitless number. Okay, so we've just rearranged this this equation for quality of Y average is equal to Y sub F minus X Y sub F G. We've rewritten that equation here, where Y can be any property, and this V is our V average, to solve for the quality. Okay, hopefully that makes sense. Okay, once we have the quality, now we can determine the enthalpy of the water. So we can look that up again in the property tables. We can look up H sub F and H sub FG, and then just plug them into this equation. So H sub F is 504.71, H sub FG is 2201.6. So we multiply by the quality and we get this value for our enthalpy. So again, this is like the H average or the lump sum enthalpy when we take into account the properties of both the liquid and the gaseous state. Okay, so now we want to figure out the volume that's occupied by just the vapor phase. So we know the total volume of the container is 100 liters, but we want to determine how much of that is taken up by vapor, and then the rest we would assume would be taken up by the liquid state. So again, another relationship for quality is that it's the mass of the vapor over the total mass. So if we want to solve for the mass of the vapor, we just rearrange this equation in terms of the mass of the vapor. So we have our quality multiplied by our total mass to get the mass of the vapor is 0.107 kilograms. Then we can multiply our volume or multiply our specific volume of the gaseous phase by the mass of the vapor. So the vapor has some quantity that has this property value. So the vapor all within the system has the same property value that exists along the saturated vapor line. So multiplying, we have our mass of our vapor multiplied by the specific volume of a vapor at that pressure and temperature, and then again we convert it back to liters. So it's not taking up a significant portion of our system. And I think maybe there's a calculation error there. Just one moment. Let me look at that. Yeah, that's actually 94.78. Apologies. See, I looked at that and I thought that doesn't look right because the vapor should be taking up a significant portion of the container even though it has a small mass. So I forgot to multiply by 1,000 when I was putting this together last night. So apologies for that. It's 94.78 liters. So in a 100-liter container, there's a very small portion of that that has been converted to vapor, but it takes up a large, significant portion of the container. Okay, let's do another example, similar example. Now we have an 80-liter vessel, which has 4 kilograms of R134A at 160 kilopascals. So we want to determine the temperature, the quality, the enthalpy of the refrigerant, and then the volume occupied by the vapor phase. So it's the same things that we were solving for before. This is just an additional example of that. Now using instead R134A. So R134A, the table that we need to look is table A12. So that's again in your appendices. That's in the back of the book, and make sure you're looking always at the correct substance for your property values. So we first again need to fix the state. So we need to solve for the specific volume. We look up, or we solve for the average specific volume by dividing through by the mass, the volume divided through by the mass, and then converting to meters cubed per kilogram. So we look at 160 kilopascals, as was given to us in our problem statement, and we find that our V sub F and our V sub G are those two values. The value we solve for, this 0.02, falls within that range. So we know we have a saturated liquid vapor mixture. So the temperature is just going to be the saturation temperature of negative 15.6 degrees Celsius. The quality, again, can be determined from this relationship. So this V average minus V sub F divided by V sub FG. And again, quality is a unitless term. So we find our quality to be 0.1569. And in other words, that means like 15.7% of the vapor, of the mass has been vaporized. Continuing, we can look up the enthalpy, where our H average is equal to the sum of this H sub F plus X, or the quality multiplied by H sub FG. Again, we're just looking up these property values in the table at that saturation temperature and pressure, and then calculating the value. And then from the quality for part D, we can again determine the relative masses of the liquid and the vapor. So the mass of the vapor is going to be equal to the quality multiplied by the total mass in the system. So of 4 kilograms in that system, only this much, 0.6276 kilograms, are in the vapor state. So it's about 15.7% of it. And then solve for the total mass by multiplying the mass of the vapor by this specific volume that represents the property values of vapor at that temperature and pressure, and then converting to liters so we can compare to our original value. So again, it's a small quantity of vapor in terms of the mass, but it encompasses a significant portion of the pressure vessel, of the vessel, which I think was 80 liters. So it's like 15% of the mass, but it's, you know, like 90%, 85% of the volume. Okay, so that's all dealing with property values underneath the dome or in the saturated liquid vapor region. So now let's look at superheated vapors. And if we compare them to a saturated vapor, there are certain characteristics that apply. For example, they will have a lower pressure at a given temperature. Okay, so the pressure of a saturated vapor is higher than that of a superheated vapor at a specific temperature. They will have higher temperatures at a given pressure. So you can either lower the pressure or increase the temperature to go from a saturated vapor to a superheated vapor. They will also have higher specific volumes. So as the density increases, as we add more energy to the system, the molecules are moving further apart. So their specific volumes are going to be greater than the same fluid at the same temperature if it's a saturated liquid or a saturated vapor. And then they'll have higher internal energies, again, because there's additional molecular movement, and higher enthalpies because they are a higher energy state. Okay, so you need two variables to fix the state, similar as to before, but this time you can use temperature, pressure, or specific volume, because temperature and pressure are not dependent for a superheated vapor. They are only dependent for a saturated liquid vapor mixture. So looking at the superheated tables, we looked at these last time, that the pressure and the saturation temperature is given. So this first row here gives this, it's the saturation temperature for each pressure. So in this case, the saturated temperature is 45.81. Here it's 81.32. And here it's 99.61. Okay, and you notice that there's this gap here because at a temperature of 50 Celsius, we do not have a superheated vapor. We have a saturated liquid vapor mixture, most likely, because we'd have something less than that because we're below the saturation temperature. We'd have a subcooled liquid. And then the same thing here, that because we're below the saturation temperature at 50 degrees, we don't have a column. Whereas at 100 degrees, we're just slightly above the saturation temperature, so we do have property values at that point. So let's just do an example. We want to determine the temperature of R134A at 100 kilopascals and 275 kilojoules per kilogram. So in this case, we have pressure and enthalpy, which again, enthalpy is an independent intensive property. Do you like my writing? It's independent and it's intensive, meaning it doesn't depend on the extent or the size of the system. So enthalpy is another one that we can use to fix the state. Generally, however, if you're running experiments or you're trying to determine property values, enthalpy is not one that you often look up or measure. Usually you're measuring the specific volume or the volume and the mass. So usually in real life, we're not given an enthalpy, but we'll be given a specific volume, and we use that to fix the state. But, you know, in the property tables, you can do it either way. And in this case, That's what's given to us, so that's what we use. So let's again look in the tables in the back of the book. So we can look at table A12 for our R134A. Oh, not A12. Sorry, it's going to be superheated, so it'll be A13. That our pressure was 100 kilopascals, so 0.1 megapascals, and our enthalpy is 275. So if we look on this table, we actually find that we're in between two columns for enthalpies. So 272 and 280, we're in between those two. So we have a superheated vapor, but we have to figure out what is our property. So we have at 20 degrees Celsius that the enthalpy is 272, and at 30 degrees Celsius we have 280.69. So we look above and below our desired value of 275. Okay, 275 is the value that's given to us in the problem statement. So we have to figure out what is the temperature. Well, we do that by interpolation. So T2 minus T1 over H2 minus H1 equals T1 minus, or T minus T1 over H minus H1. So again, we're just looking at points along a line. So if we know at 20 and 30, we have certain enthalpies. So at 30 degrees, it's going to be something like that. At 20 degrees, it's something like that. So all interpolation does is draw a line between those 2 points and say, all right, I know that I'm somewhere along this line. I know my enthalpy is here, so then I can just read and figure out what is my temperature there. Okay, so this would be like H1, and this would be like H2, and then this is the H that we're given in our problem. Okay. So then we can find our unknown temperature by interpolation. Okay, and that turns out to be 23.35 degrees Celsius. And this is a good point to do a reality check. So you go back to your original temperatures and you see, okay, 275 is closer to 272 than it is to 280. So what I would expect that my temperature would be closer to 20 than it would be to 30. So it's always a good idea after you've done this math to go back and make sure your answer makes sense. First of all, it needs to be between these two temperatures. And then second of all, you can kind of look at it and think, okay, that seems right. I haven't done any miscalculations. If I were to come up with a temperature of like 50 degrees Celsius somehow in my math, my finger slipped on my calculator or whatever, I could go back to this and think, oh, that doesn't make sense. It should be between these two values, not greater. Okay, so let's do another example of that. Determine the temperature of water when we're given P equals 0.5 megapascals and H equals 2890 kilojoules per kilogram. So again, we have two independent intensive properties. Whether we're in the superheated region or under the dome, they would be independent. Because we're doing superheated examples, we can presume that it's going to be superheated, but it's always a good idea to double check. So at 0.5 megapascals, H sub G is 2748.1 kilojoules per kilogram. So if we were to go to the water table A5 and look that up, so at table A5, or on table A5, looking at the saturation enthalpy at 0.5 megapascals, we would see that it's 2748.1. Okay, so 0.5 megapascals is equal to 500 kilopascals. So again, from table A5, we can look that up and see. And I hope you're following along with these examples and actually looking at your property tables, because I think it's helpful to learn how to do this, seeing the examples along the way. Okay, so then because we're a superheated vapor, we now move to table A6. So at 0.5 megapascals, we have T1 and T2, H1 and H2. And our enthalpy value, oh no, that's not the right one. our enthalpy value as given in our problem is 2890. So it's in between these two values. And again, we look at it and we think, okay, which one is it closer to? Is it closer to 2855 or 2961? And I think it's closer to 2855, or actually it's pretty close to in the middle of those. So as we do our interpolation, we find that our temperature is 216.3, which is about what we would expect. Okay, so it's not quite 225. It's not exactly in the middle, but it is closer to 855.8. So it makes sense, and that's good. All right. So now let's look at the compressed liquid region. So compared to a saturated liquid, so again, if we're looking at the dome, this is a superheated vapor, this is a saturated liquid vapor, this is a compressed liquid in these states. So the pressure line on a TV diagram is something like that. So superheated, saturated liquid vapor mixture, and compressed liquid. So compressed liquid is also just liquid water. That's what we are familiar with. So it's characterized by a higher pressure at a given temperature. So these compressed liquids, you can vaporize or cause it to come closer to the saturated liquid line by decreasing the pressure or by increasing the temperature. Okay, so compressed liquid is going to have a higher pressure and a lower temperature than a saturated liquid. It's also going to have a lower specific volume, which physically you can see, and it makes sense that as we start adding heat to this fluid and it becomes closer to vaporizing, that the density is decreasing and the specific volume is starting to increase. It has a lower internal energy. Again, liquid is is the lower energy state of a fluid, liquids, and then solid is even lower energy than that. And it's going to have a lower enthalpy, again, because it has a lower specific volume for a given temperature or pressure, that there's less internal energy, but there's also less potential for expansion, or less expansion happening as we proceed through the compressed liquid state. Again, we also need two variables to fix the state. Temperature, pressure, and specific volume are often very good ones to use. The compressed liquid tables, as seen before, again, give us a pressure and then also the saturation temperature. So if we're lower than this saturation temperature, then we know that we're a compressed liquid. So again, you can see that the column doesn't continue beyond 260 because 260 is the last number that's lower than this saturation temperature. The same you can see for 311, that it goes up to 300, and for 342, the column goes up to 340 degrees Celsius. Okay, so anything at a higher temperature than 342 is no longer going to be a compressed liquid. It's going to be saturated or superheated, depending on the specific volume as well. Compressed liquid properties don't really change very significantly from saturated liquid properties. So once you liquefy something, once you have removed the energy and you're in the liquid state, the density doesn't change very significantly as you cool the water, nor does the specific volume, which is the reciprocal density. So if we don't have property tables for a compressed liquid, we can often approximate them as a saturated liquid. So let's say we actually want to know the property value of something here. We can say, okay, at that same temperature, we can look at it here and just read over to find the saturated properties at that same temperature. The one exception is enthalpy, because enthalpy is dependent on specific volume and pressure, but we can still use the property values to approximate it using the property values at the saturated liquid state. So we look up the enthalpy of the fluid at that saturated temperature and the specific volume of the fluid at that saturated temperature, and then the pressure that it would be at that saturated temperature. Okay, so then we use this pressure, the pressure that we're currently at, minus the saturation pressure at whatever temperature we're at. and multiply it by the specific volume to give us sort of a correction factor for this enthalpy. And we'll do an example of that, I think, in a minute that shows how far off it is for us. So here's another way of looking at it, that we assume like we're a compressed liquid here. Let's just say we don't have property tables that tell us exactly what our property values are there. We can say, well, I don't know what it is there. I'm just going to approximate my specific volume as the specific volume at this saturation temperature, because I do have a property table for that. And these lines are fairly close together. It's expanded and sort of blown out on this particular diagram, but in reality it's not off by very much. So let's just do an example of that. We're going to see the error involved using data from the compressed liquid table versus the saturated liquid table, and then calculate the error. So if we know our temperature and our pressure, we want to find our internal energy. So from table A7, we can look it up directly. So with a pressure of 5 megapascals and a temperature of 80 degrees Celsius, then we just look up the internal energy. So this is the compressed liquid table. So this is the actual value. This is in reality what it is. In part B, we now go and look it up on the saturated liquid table. And it's very important that you look it up at the same temperature. Okay, you don't look it up at the equivalent pressure, the same pressure. You always go to the temperature table and look it up at that same temperature, because if we look back to this diagram on a TV diagram, that's where we're making the approximation. So if we want to know the specific volume for something at this temperature that's a subcooled liquid, then we have to approximate it at the temperature of a saturated liquid. Okay, we don't use pressure, because at the same pressure it's actually going to be this value up here, because that's the constant pressure line, and it just really messes things up. So again, only look at it at the same temperature. So if we calculate the error, it ends up being 0.34%, which is a pretty good approximation. To only be off by that much, that's 0.34%, not 34%, like the decimal's in the right place there. So it's a pretty good approximation. It wouldn't provide too much error, and that's fine. Okay, hopefully you're gaining confidence in using and looking at the property tables. This is just one last example that I wanted to get you started on your homework. So problem 329 is actually a homework problem, and I wanted to give you a little hint and a head start on that, because there is a little bit of tricky stuff in it. So in this problem, you have a piston cylinder device, and it has R134A as the working fluid at negative 10 degrees Celsius, and there's 0.85 kilograms of it. Okay, so the piston is free to move, and it gives you the mass and the diameter of it. Okay, the first thing you should know is that when it said the piston is free to move, in other words, as this gas expands, the pressure will remain constant. Okay, so the gas right now is contained within this piston cylinder device, and it's already balanced the weight of this piston to give us whatever the pressure is. Okay, so we know the local atmospheric pressure is 88 kilopascals. What we have to figure out is, in combination of the weight of this piston plus the atmospheric pressure, what is the pressure inside here? Because we know the mass and we know the temperature, but we don't have another independent property to fix the state. So we're going to have to calculate the pressure. So to fix the state of the refrigerant, we need to know the pressure inside. So we would perform a force balance like this. Okay, so we know that the pressure inside has to be equal to the pressure outside plus the weight of the piston, or the pressure due to the weight of the piston. Okay, so for force balance, knowing the diameter of the piston and that it's a circular piston because it has a diameter, we could calculate the surface area and figure out, due to this atmospheric pressure, how much force is being exerted, and then add it to this force to figure out the upward force due to the pressure inside. And then again, knowing the diameter, convert back to the pressure. Okay, so I've done that for you. Please do it yourself and make sure you get this same answer. Okay, so this will fix your state, but do not skip steps and don't just copy this. Do it yourself. This just gives you an idea of how to do it. I'm giving you a leg up on this one because it has caused problems in the past. Okay, so you should be able to find that the pressure inside the vessel is 90.4 kilopascals. Now, determining the rest of the problem is up to you. So you have to determine the final pressure, the change in the volume, and the change in enthalpy of the refrigerant. So you need to be able to look up everything at the initial state, figure out based on the temperature change, what is the final state. Okay. So again, remembering this is a frictionless piston, so the gas is allowed to freely expand. We've already found the initial pressure. You would have to know, wink, wink, nod, nod, what is the final pressure of a piston cylinder device where the gas is free to expand, and then look up the property values at both states to solve for what is required. Okay, if you have any questions on that, please just send me an email. Please look at the property tables, make sure that you understand how to look up things. And if you have any questions or have any problems, please come see me and in my office today. I guess you're probably not watching this video before I'll be in my office, but I'll be there from 10 to probably 1:30. If you need to meet me at another time, send me an email. We can meet up a time or set up a time for next Tuesday if needed. So good luck, and that's it.